In this problem, we're going to be looking at dispersion. Dispersion means that light of different wavelengths has a different index of refraction traveling through a material. All right. So as different wavelengths of light travel through material, they're going to interact differently with the material because there's a different index of refraction for each individual wavelength. So there's a different index of refraction for each wavelength. So white light has several indices of refraction because it has different wavelengths of light. And those are going to each have different index, going to have a different index refraction per wavelength of light based on the material. So let's read the problem. We're going to have red light whose index of refraction is 1.520, and violet light who's going to have an index of refraction 1.538, and it's going to travel in air, which is going to have an index of refraction of 1. And then it will be incident on a slab of crown glass. Both colors are going to exit the glass at the exact same angle of refraction. The red light is going to have an angle of incident of 30 degrees. What is the angle of incident for the violet light? So this is going to be the angle of incident for the red light. We're going to want to use Snell's law for this. Snell's law is going to be N of the air, and we're dealing with the red light. We're going to deal with the red light. Sine of theta, index of refraction, is equal to N for the red light, sine of theta of the red light being refracted. And this is going to be the light in the air. This is going to be the light in the crown glass. Now the air is going to have an index of refraction of 1.00. Sine, the angle of incident for the red light is going to be 30 degrees, is equal to the index of refraction for the red light, which is 1.520, and then the sine of the angle of red light that is refracted. Therefore, our theta, RR, is going to be equal to 1.00 sine of 30 degrees all upon 1.520. Oh, this should be the sine of theta RR. Sorry, I forgot about that. We do this calculation, and we're going to find out that this is equal to 0.3289. Therefore, our theta RR, so this is the angle of the red light that's refracted, so the refracted angle for the red light is equal to the inverse sine of 0.3289, and that happens to be equal to 19.20 degrees. All right. Now, per the instructions, it says that both colors exit the glass at the same angle of refraction. So what that means, what that's going to mean is it's going to mean that the angle of red light refracted, which is equal to 19.20 degrees, is going to be equal to the angle of the refracted violet light, Now, we can use Snell's law once again. And so this becomes, oops, I got this backwards. This should be VR, so this would be the violet refracted light. We know then that the N, the index of refraction of the air, sine of theta, this is going to be the incident violet light, is equal to N of the violet light times the sine of theta VR. VR is going to be the violet refracted light. So let's start filling this in. And we know this angle right here. So this is 1 sine of theta IV, incident violet light, is equal to the index of refraction 1.538, index of refraction of the violet light. And this is the sine of the theta, or the angle of the violet light that gets refracted. That's 19.20. So our sine of theta of the incident violet light is equal to 1.538 sine of 19.20. We can do this arithmetic and we get that theta IV, so the incident violet light, is equal to the inverse of the sine of 1.538 times the sine of 19.20. It's going to be the inverse of that entire quantity. And when you plug that in, you get an angle of 30.39 degrees. So the angle of incident is slightly different than the angle of incident for the red light as it is for the violet light. If you have any questions on dispersion or any problems that pertain to that, please let me know.